Hi. Hi, Omni. And hi, eDog300. Good to see you as well. Alrighty, so today we are going to be playing with the CAN add-on board, which we have designed in previous streams, assembled in another one, and today we're hopefully going to get working on some gateware. A CAN, exactly. I was a little bit stressed just before the stream started because I suddenly thought that my tools had failed me, but thankfully I've got a solution so we can continue. So yeah, fundamentally this is a CAN board. I'm sure you're all aware of what it is. We've got some nice silk on the back to show how the pinouts go, and you have two CAN channels brought out to these nice spring-loaded terminal blocks and to the DB9s, which means that you can just plug in a vector CAN or an OBD2 adapter, depending on which channel you use and the default configuration. And there's also some in here, there's some jumpers which you can cut and rewire in this little patch panel to suit your needs. No tools because they weren't behaving, but I think I figured out why they weren't behaving, and that's largely to do with termination. So yeah, I was scratching my head for a minute, and it was just not working, and there we go. So they're not official tools or proper tools. They are projects that I've done with my professional hat on, and so some of them are with some gummy firmware, some just very proof of concept level firmware, and they need somebody else on the line to acknowledge the packet, otherwise it just sits there going over and over again, that kind of thing. So yeah, we have some tools. We have here a CAN add-on and a Glasgow. And the idea being that you just take one of these ribbon cables and you connect them together, and job done. I had originally wondered about putting the CAN add-on on top, but because of the size of the connectors and various other things, that just wasn't going to work. So there's that. This is one of the boards that I'm going to use today. It's got a super bright LED on there, but it has a CAN interface here, which we're going to wire up to the Glasgow. And then I've got another board off screen which will acknowledge this. So this one is going to be sending the messages so that we can get something to receive and to work with on the Glasgow side, sorry. And then the other board will be acknowledging them so that the message goes away, goes off the bus, and it carries on nicely. I've also got the scope wired up so that we can see what's going on. And I think first things first, I'm going to put this onto my notebook just to save my desk, just to demonstrate these spring-loaded pins, because they work. They're much stiffer than I had hoped, but they do work, which is nice. And when you push them, I'm not sure if you'll be able to see on stream, but when you push them, it opens up a little hole, and you can just feed the wire in there. So if we bring this board closer, what we're going to do is put the ground in like this. That goes into the 0-volt hole. And then we've got the CAN high and CAN low. So that's nice and simple to just hook it all up. There you go. The termination I mentioned I needed earlier, so I've just been through this process very briefly off stream. Hey everybody. J Kiv. Nice to see you. Yeah, so the termination I mentioned previously, I'm just going to fit that in here, just so that it's got somewhere to live. And then that will just sit there. So there's a 100-ish ohm resistor. You won't quite be able to see that. It's just there. J-Kiv, good. Sorry, I'm a bit dyslexic, so I struggle with words that I've not come across before. Right, so that's that, and then I've got my scope probes here, and they're just going to be wired up to the patch panel, or whatever you want to call it, in the middle here. We've got the common ground, we've got the CAN low, which is white, and CAN high, which is blue, and these wires will also then connect off to a board off screen, which will acknowledge and respond appropriately, and it will also let me just confirm that the messages are going out properly. Pulsing RGB, yeah, it's very bright, so I don't think it will blow out the picture, but might have to be careful about that. That RGB one just means that CAN channel's not active, because otherwise the LED would blink as it transmits and receives. But yeah, I'll just leave that there-ish. Okie dokie. So if I grab the scope up, you won't be able to see it very big at the moment, but if I send a message, you might see that the red LED on this little board here blinks every time I send. And we also then get some action on the scope. This one, there we go. So there's the CAN message, and I'm just sending to address 123, the single byte 11. And I'm going to send 12, and there you go, 13, etc. So that gives us the ability to put some data out on the CAN bus that we can then hopefully work with in Glasgow. So I'm just going to get rid of that notebook now because I'm on to draw on it in a minute. There we go. And I'm going to plug Glasgow in. That's not the right wire. Where's it gone? Here it is. Oops. Excuse me a second. My other desk is horrible at the moment in terms of clutter and cable management and stuff. There we go. Here's a micro USB cable for Glasgow. There you go. Now I haven't actually turned this board on yet. We got to the end of a stream having just assembled everything, and I've done nothing else since. We did unfortunately have a missing component, so the termination LED is not going to work. But I have actually got something, so why don't we just fit that really quickly? Let's just put that in. My book, soldering iron. And by book there, sorry, I meant a book of surface mount resistors. There you go. We've got all sorts of values here. I didn't parallel the two resistors, no. I didn't quite have enough. I ordered sort of the right number, which was a bit foolish, but never mind. So if we just refer back to the datasheet. Oh, not the datasheet, sorry, the schematic. I think it's here. There you go, so we got the termination LED. I think it was a 30K, something like 25K. I'll just flick through the book. I think that will be 27K, let's just go with that. What I've got available. Oh, hang on, no, sorry, I remember now. I reworked the BOM because the LEDs were not so available. So the BOM, the ordered BOM, here we go. So it's R3, R3 is 30K, okay. I have got a 30K, let's just do that then. These. Put it back down on the desk. I'm going to get my soldering stuff. Unfortunately, the camera is now back in the normal position, which means that you won't be able to see what I'm doing anymore, because it's a bit of a reach for me. So let's just... Actually, maybe I'll see what I can do in terms of reaching. Wetting the sponge quickly. I'm going to disconnect all of this so I can yoink it. There. Yeah. Need some tweezers. On the face camera, and you can see me. It's not exciting, I'm afraid, but let me just do this really quickly and then we'll get back to it. I'll do both of them, I think. Shouldn't take long. All right. One down. There you go, not pretty, but that'll do. Hey Esden, thank you for joining, good to see you. Hope everything's going alright. I was just taking a minute to solder in the components we were missing from the build the other day. It is out of view, yeah. Unfortunately, I had the camera on a special arm out in front of me so that I could do the assembly. I just wanted to finish that off really quickly. So it's yeah, it's just back in where it normally sits now, the camera. I think I'd like to have another one set up, really, that'd be nice. All the cameras. Okie dokie, let's put that on the floor. Great, there we go. So back to here, let's plug it all back up again. Hopefully the termination LED will work now. Not that we've tried it and it hasn't worked yet, but you know. So again, the ground goes in. The can high is this one. Let's do can low first. It's that one. Okay, we've got the ground for the scope. And then we've got the can low and can high. Okay. Oh, and I've got to do the termination resistors as well. I love that video so much, the square hole video. It's just silly. What are we doing here? Come on, in the hole. Better. Okie dokie. I think we're done. So back to the scope. If I just send a message, that happens nicely. Okay, cool. So, just some gateware. Okie dokie. Just grab away some of these things. I think we made a start on something the other day, didn't we? Can sniff. I'll do. Oh, that was unexpected. Oh dear. This is where we have a major diversion while Atty goes to figure out what's going on. was very unexpected. What have I forgotten about? Sorry, everybody. I think it might be something Docker related. That's kind of annoying. Just gobbled up all of my disk space. Okay, let's do something else in that case. This is on a different file system, so hopefully we'll have enough space there. Grab a copy of Glasgow. Need to get the URL. I don't think we got very far at all, so let's just pretend it's not there and keep moving. So interface can sniff. And we're just going to copy something else, so I think the UART one's probably reasonable to copy for this one. We need not all of this stuff. Let's just cut a bunch of it out. I can never decide what to do when I'm starting afresh. Okay, let's call it the can sniff applet. Communicate via can. So let's reword that, it's just receiving via can. Okay, and then now if we refer back to the schematic, each channel has a receive, a transmit, and a terminate pin. So RX, TX, and let's call it term, just to keep in keeping with the rest of it. There's no parity. There's a bit rate, so it's not referred to as baud rate, I don't think, in CAN really. So let's call it bit rate, and the default I'm going to put as 2250K. Tolerance is fine. Invert, transmit, receive. I'm going to remove them just to keep it simple for now. A lot of this should be pretty common. So in terms of figuring out baud rates, later we might be able to auto-detect that as well. But for today, I think we're just going to keep a keen eye on just receiving data initially. Hopefully I'll be able to enable the termination, the onboard termination, and remove that resistor as well. That'd be cool. But small steps, one by one. Right, don't need parity. Don't need the auto stuff yet. Don't need the use auto. Don't need the inversions. Non-arguments. Don't have any polls. I don't want the auto boards, that's fine. We can just get rid of that entirely, I think. Okie dokie. Don't want any polls, go away. Don't want auto board. Just a matter of stripping everything out right now. Interact arguments. We're going to have none. So if we refer back to another applet, like video VGA, I think, that should give us a guidance on what we can do here. I don't think we actually probably want any interact arguments, to be honest. Yeah, we can just omit it. It's fine. Don't want these, don't want that, don't want that. And then we end up in interact. Let's keep one of these just for reference. Don't want a task, and we're going to, as I said earlier, keep that for reference, so we can just move that directly through. Best way to start out is to copy something. Hope I'm not alone in thinking that. Okay. Right. What are we doing now then? In the interact phase, we want to receive messages from that FIFO and print them out onto the screen. I'm kind of tempted to just do nothing for now and sleep for forever. But we'll come back to this, I think. So that's fine. Okay. So we've got the bit rate and a tolerance, and that's it for the moment. We will be able to configure pins later. That's already given to us for free by that. That's cool. Let's make a... Right, okay, because this is the UART, it's importing stuff from the generic gateware. Gateware UART.py, and there's this UART bus class. So we're going to want one of these, but let's just put it in here for now. CAN bus. And in here we're going to outline the pins associated with the CAN bus. We don't have anything else. Transmit, yeah. So this is where we need to start referring to data sheets. And we've used the TCAN, what was it called? Yeah, TCAN 1051. There we go. And this has got, as I said earlier, transmit, receive, and it's also got a silent pin that we're not using. So if we come through and find out what these pins need or expect, the transmit, it's low for a dominant and high for recessive bus states. Now CAN operates, CAN bus, let's see if we can get the wiki page up. CAN operates in what's called dominant and recessive states, and you can see that here. So the idle state is recessive, it's where the lines come together. And the dominant state is where it pushes CAN high up and it pulls CAN low down. And this is kind of somewhat equivalent to open drain, so I2C, that kind of thing, where a number of people can assert a dominant state on the bus at once, but if nobody's asserting the dominant state, then the bus just sort of naturally goes back to the recessive state. So idle is the recessive, and these actually then translate the other way up to the way you might expect. So the recessive state here is actually a logic 1, and the dominant state is a logic 0. This means that if we want the CAN bus to be recessive, and for that to be a logic 1 in our gateware, then we need to set this such that the transmit signal is probably inverted. Is that right? So low for dominant, high for recessive. Oh no, that's okay. So it is positive logic on this pin. So high is recessive, so that does an inversion inside the gate, inside the part. That's cool. We then also got the termination pin. What am I doing? Term I. And the way we've drawn this is that if the termination signal is high, then the LED comes on here, but also importantly the diode, the photodiode inside, or the LED inside there, also turns on. And turning that on will cause the termination resistor to be put in place. So that's a positive logic pin as well. So here we want to reset it to 0, I think, and default to termination off unless the user explicitly requests that it's turned on. Okay. So the transmit pin output enable is equal to 1. So that's a simple thing to put in there. The output, also the transmit pin is then equal to self.transmit. Apologies, that should be an O. And that should be an O. So the receive pin turn on, the receive pin output enable is turned off. Yeah. And actually what we're going to do here is RXI is equated to self.rxt.high. You'll see here that we've got the FF synchronizer, and what that actually helps to do is make sure that, what's it called? Astable? No, not astable. I can't remember now. But make sure that the signal is clean effectively when it crosses gate boundaries or clock boundaries, because otherwise you end up with potential sort of noise and indeterminate states. I can't remember what it's called now. Never mind. So because they are using, I believe, the input directly into the counter, is that right, to count the clocks, or the length of the bits, that's probably important. I think it might well be important for us to do as well. So I'm just going to copy that. Metastability, thank you, yes. Reading my mind. Generally a good idea on inputs, I think. So this changes this line out then for, nope, not that. Oops. And again, I think this is going to be, where is it? Low for dominant, high for recessive. So that's positive logic again, which is good. Which means we can put a reset equals 1 on that. And that should hang together. The termination then. What is CAN? Oh, I've glossed straight over that. CAN is a communication protocol used a lot in vehicles and other noisy environments, electrically noisy environments. It's kind of like a UART, if you're familiar with that, in that you can send sort of individual, well, you can't send individual characters with CAN, you have to send an entire frame or packet. And it's a differential signal, which means that it's got better immunity in noisy environments. But it's also got other things which are kind of neat in the way it deals with the arbitration of packets. So a packet with a higher priority will always get to go first, and the priority is kind of baked into the ID of the message, if that makes sense. Oh no, you can go up to 8 bytes, I think it is, 8 octets in CAN messages, and then there's obviously the extended CAN FD and all kinds of other stuff as well. But we're just going to focus on simple CAN today, up to 8 bytes, 8 octets. There you go. Came from a web dev background. Microcontrollers and electronics, great, welcome. It's a really enjoyable place to be, I think. I like it a lot. If you do have any other questions, please feel free to pop your head up and do ask away. Yeah, no worries there. Omni. So this is an example frame, but you can have this red bit is the data field, and everything else around it is addressing and error checking and whatever else you want to call it. But this data portion, this data field, can actually be up to 8 bytes long. Yes, this is when I typically stream. Wednesdays at about 11 o'clock UTC. Ah, sorry, Omni. Okay, we're probably talking cross purposes, saying the same thing over and over again. Yes, CAN behaving like a won't bust. So, not sure if you're here at the beginning, Ed Borden, but I was fighting with my tools trying to get this working. I think I have a schedule on my Twitch page, don't I? Yeah. Twitch.tv/grand, I think it is. It's going to be a bit loopy. I don't know how to see my... Does this only happen when I'm not streaming, maybe? I'm pretty sure there's a schedule there. But yes. Wednesdays at 11 or 23 UTC. Anyway, right, so so we're going to do the termination pin now. Like that. Oh, well done. Thank you, Peter. Right, so this module here will just take care of wiring up simple signals to pins. And as you may have deduced now, a pin has an output enable flag. It also has an input flag and an output flag. And we don't actually care about all that complexity. We just want to make use of the signals as they stand. So this module here just deals with that for us. The framing is expensive, but because of what CAN is and how it works, it's actually, if you think about it, the reason it's used in an automotive environment, so that's vehicles, cars on the road, lorries, etc., trucks, is because it's kind of safety critical stuff almost. So there's very good error checking, but there's also arbitration in terms of if a higher level packet, or an emergency packet, almost like something about the braking system, for example, is trying to get through, then it can just talk on top of everyone else, which is pretty cool. I'm just going to get rid of all this ordered board stuff because I don't care. Not yet, at least. CAN sub-target. Out FIFO, in FIFO, parity. Let's have a look. That's the UART still. So what we have given in, this is the UART sub-target here. And we actually need to rename that to CAN sub-target. Multi-master and all that, or whatever you want to call it, that kind of thing, yeah. So while CAN doesn't address messages to people, the contents of the packet or the frame is identified by its ID. So you might have the braking system with a flag saying whether or not ABS is active, for example. and that ID will always be paired with a fixed set of fields in its payload. So it's not necessarily sending a message from A to B. It's more that A, as in the ABS system, is just transmitting its state over and over again, that kind of thing, typically. Lots of people misuse it, though, and you can get sort of two-way communication between points and that kind of stuff. But that's kind of not really normal, I don't think. Right, can sub-target. So we're going to get rid of the parity. The max bit cycles, we don't want that either, so I'm just going to get rid of that from here as well. That's to do with the auto baud rate and building the gateway and stuff. That's that. We got the manual cycle, so we're going to use this to determine the timing for each bit. That's now defunct. That's defunct. That's kind of feedback. I guess we can keep it. And the invert of the transmit receiver dead as well. How does that look? I think that's okay. Now, this will instantiate a UART again. That's abstracted away into generic gateware, which means that anyone can just produce a UART. We're not going to do that today. We're just going to implement, I think, everything in here for now. Don't want either of these, and it's probably time to just get rid of everything else. So, how exciting. Having said I'm just going to delete them, yeah, I'm going to put in a new bus. So, self.can bus equals. And we're going to pass in the pads. Oops. So first things first, I think we should try to turn on and off the termination, and we should try and assert and deassert on the bus as well, because that will give us sort of confidence that the hardware is working, because as I said earlier, I've never turned this on before. So I hope it works. So what we're going to do first up is try the termination. So that would be self.can bus dot term o dot equals 1. All right. I didn't give the termination a reset state, did I? Hang on a second. Oh, they're up there. Yeah, that's fine. Getting all confused for a second. Okie dokie. Can sub-target. That's just going to sleep forever, and hopefully it'll turn on the termination. Fingers crossed. I'm going to get a new tmux terminal, because otherwise I will get lost everywhere. And because of the whole disk space issue, yeah, 139 gigabytes in Docker. Let's come back. Oops. Because of the whole disk space issue on the other system, I'm going to have to install everything afresh now. And I keep notes in a kind of a wiki notebook, whatever you want to call it. In here, so we go dev boards, Glasgow, Glasgow.md, here we go, and this is how to install it. So I'm just going to kind of copy and paste these across. Um, 3.8, new virtual environment. Okie dokie. That's easy enough. This command will get the latest FPGA toolchain. No, it won't. Cannot iter over null. What's wrong with that then? What? That'll do. Let's put a -L in there, update our docs. Might have to update that more completely later. That doesn't look right. Oh no, it's just reading the URL, isn't it? So that looks happy. Grab it. Apologies for this, I wasn't expecting to have to reinstall everything. I'll have to dig into that later, I think. So have we now got... No, we haven't extracted it yet. That helps, doesn't it? I should really look into, I can't remember what it's called, ASM, WebAssembly, is it? WASM? I've not even looked into it yet. But I know White Quark's done a pretty good job on getting that, getting that up and running, so it's much easier to get going with. It is WebAssembly. Okay, I thought it was. There we go. Okay. That's that. Now we need to get us the Glasgow stuff. So if we go into Glasgow and do software, Python 3, setup, develop. And just like that. There. So the CAN add-on is because I feel like it's a neat project and I kind of want one. In terms of Glasgow more widely, then that's sort of brainchild of White Quark, and she's very keen on open tools and open software and everything else. So yeah, I don't know how else to put it. It's out there because it makes most sense for everybody to have it. And I suspect if it wasn't public, then it wouldn't have got to where it is today, you know, if she kept it to herself, for example. Does that work? Yeah, I like it. It's good place to be. That's not what I expected to see. This is number 714. This one. I haven't added it to the global thing yet, have I? So that needs to get added into there. Let's put it in here. So in the all applets, you need to add your applet in here. Alphabetical, please. I'm just going to call it the CAN applet for now, but it'll come through. Let's go run help. That should show us. Oh, can't do it. What have I called it? Oh, CAN sniff applet. I did call it CAN sniff. CAN sniff applet. And I called it CAN sniff. That should be, there it is up there. Very cool. So if we try and run CAN sniff again, it says no. Why does it say no? Oh, I didn't do run. Run CAN sniff again. Oh, sorry, I'm being a right muppet. All these arguments are in the wrong order. There we go. So we're going to go for 5 volts, I think it is. Just check this schematic again. Yeah, 5 volts. That's just up here on this pin. And that's the Glasgow is going to provide that power. So you see Glasgow turns on. I'm not sure if you can quite see that. Ooh. And it's turned off again. Right, so I had an error in my code. Line 103. args.board. Okay, that needs to change out for bit rate. There you go. Gonna work. We can see now that the green LED here has come on. I'm not sure if you can see that. I'll shield it from the light a bit. There you go. Green LED's come on, which means that the port is now powered. But the orange LED over here hasn't come on, and it's actually not warm even. So let's try inverting that logic. Let's see what happens. I don't think it needs inverting. Oh. I haven't assigned it pins, and so it's all over the place, isn't it? By default, we have got the receive pin on 0, the transmit pin on 1, and the termination pin on 2. And that's, I think, not what we want. What we actually want is this, which means transmit, receive, and termination. So those two are backwards. Let's fix that here quickly. Just swap those two around. If we do that again, so it's transmit, receive, termination. Transmit, receive, termination. Okay. So the termination was already on the right pin, but for some reason it's not done its job. What's that about then? I think I saw, yeah, I did, very briefly. I will run it again, and maybe I'll turn the lights off a bit so that you can see, hopefully, as well. Let me just do that quickly. This one. So if I run it now, I'll run it, and you watch this termination LED down here, and it will go. I think. Nope, it's not doing it. Let's do Glasgow safe. Turn everything off. Glasgow run, watch the termination LED there. You're going to do it. No. Oh, what? Okay. Why? We've got this pinout here matches up with the Glasgow pinout, so let's just grab that up quickly. Glasgow hardware boards, Glasgow Rev C1, which is what one of these is, schematics. So it is one of these connectors here. You've got VIO on pin 2 and then grounds. And so pin 2 is connected up, pin 2 is closest to bit 0. So that's that. So bit 0 is transmit, 1 is receive, and 2 is termination for the CAN 1 channel. Why? Back on the screen again. Do port A, see if that helps us at all. I don't think it will. Probably just turn off the power from the other port. Oops. What am I going to do then? What's going wrong then? Let me just pause the webcam quickly. Get it all back in sync again. Right. Confusion, I think, is what's going on right now. Let us make that pin wheel, I think. That's probably the best idea, isn't it? m.d.sync. Oh, sorry, you're not watching the computer. So we're going to go for counter equals signal 32 bits. With dot state reset counter equals 0. So we're getting at 48 megahertz. If we want a 2 hertz pulse, it needs to be 48 megahertz divided by 2 is 24 million. So if counter is greater than or equal to 24 million, we can reset it. What we also want to do then is m.d.combinational self CAN bus termination output equals counter is greater than or equals 12 million. So that should give us a sort of a 50% duty cycle 2 hertz, I think, pulse. And we can then poke at it with a scope or a multimeter or something. I think that hangs together, doesn't it? Let's see what happens when we try and run it. Okay, so I think that's running. But as you can see, not a lot going on. So I'm just going to grab a multimeter. This is kind of quite a nice one. It's got a logic level probe on it, so it will beep when a logic low is detected. And I can go from this pad down in the corner to one of the pins on the opto there. Let me just grab the schematic quickly. Pin 1, is that identified nicely? It is, it's over there. So we can go ground to pin 1. We're going to get just a low. Always low. Okay, let's disconnect this and just back off all the way. We go from there to this one. That's not low. That is low. Oh. Let's just review the code quickly. So transmit. The schematic online, yeah, I think it's, I'll share a link for it quickly. I think it's on the Glasgow CAN repository on my GitHub. Glasgow CAN. Where can, there you go. I'll put it in the chat. There you go. So what we're doing is, we've got the receive is an input signal, transmit is an output signal, termination is an output signal. We are setting the receive output enable to 0, as in turning it off, bringing that in to there. I think that's okay. Turning on the transmit output enable, turning on the termination output enable. And we are then outputting the signals that we're giving. I suppose the next step is to try the termination output, isn't it? Sorry, the transmit output rather than the termination. Oh, I know what I haven't done. We haven't put the submodule in. Submodules plus equals self.can bus. No wonder it doesn't work. Correct. No signal yet at the Glasgow pin. That doesn't work because I've done something silly. It's not an imagine statement. Oh, right, okay. Right, very good, very good. Let's refer back to the UART again. I want to see the UART bus, really. UART.py. Right, submodules, not md.com. So this is a good start. Hopefully we're on the track now. We're actually building the thing. Created but never used. Oh, I've never returned that. It's funny when you write something fresh and then it's all just broken. Okay, that's looking more promising. So if I then poke this signal, we should get a beep, beep, beep. That's good. Cool. And if I then connect this up to the add-on board, I'll show you the camera. Apologies. What do we get? Nothing. I'll poke the corner again, but a different one. Okay. So the opto is at least beeping. Come back to here. The termination LED might be backwards. It should be pointing at the resistor. So if I just disconnect that again and do the diode test, we should be able to get it to light up. So the 0 volts should be pointing at the resistor for the termination. It's this way around. And it's not lighting. I wonder if I placed that backwards. No. What? What is going on? Yeah. That just seems to be a dead short across the diode, the LED, which is unexpected, I have to admit. How about the other side? Could be, oh, okay. Yeah, I think I must have shorted that LED while I was assembling it, so in that case we might have to shift over to channel 2 to get the termination working properly. So I'm just going to rerun now with the pin term set up for channel 2. This is a point where you realise that it might be handy to have the pin numbers written out on this schematic, isn't it? So 0, 1, 2, 3, 4, 5, 6. Pin term is 6. Is that going to flash for us? Yes, there you go. Oh, that's annoying. Okay, I'll go back and revisit that one. At least it's decoupled enough that we should be able to get the termination to actually work, even though the LED indicator is not working. I think it's shorted. Never mind. We'll come back to that one. So let's do the same again now on the transmit. Instead of wiggling or pulsing the termination, let's pulse the transmit LED. Like that. And I think we should also be able to see the effect of that on the scope as well. There you go. Ah, lovely. Lovely in green. Hopefully you can all see that okay. Hide from the light a bit, there you go. And if I now bring the scope up, like that, and because this is not going to be a valid CAN, I'm going to have to turn off triggering. That's not, not doing what I would have expected it to do. That is just, yeah. Yes, they are genuinely at the microamp range to be a decent brightness. Unlike this one here, I showed earlier, where it blinds you and lights up the room. I got that one a little bit wrong. Blinkies! This is the transmit LED, and it should be asserting itself on the bus. The only thing now I'm sort of fearful, the fact that it's not, so this is the scope at the moment, the fact that it's not asserting itself on the bus kind of makes me feel like maybe, just maybe, that silent pin is tied wrong. So, turn that off again. So the silent pin here is tied to ground. We have a look in here. Silent mode, control input, active high. Now, does that mean silent is active, or that the chip is active when it's high? I have actually got another design with one of these in, so I could check it out. Let me just grab that design quickly then. This is that other board I was showing you, and it's got the transceivers here, CAN silent, and they come through into here, CAN 1 silent, which is then up here. CAN 1 silent, PB14, so I'm going to go and check that. You would interpret it silent on is high, yeah, so low, the way it's strapped now, should not be silent. It should actually be able to assert itself on the bus. You agree? I think I might have to do this off screen, and apologies for that. Gone all quiet while I check this out. Yes, I think that should be correct. Yeah, sorry about that, Tim. I like it, and I use it for work a lot, so yeah. Anyway, I think that should be correct in terms of being strapped low should not be doing that. Now, part of the thing that these line drivers do, actually, just remembering now, is that they will pull you off the bus if you are naughty, basically. So it's very possible that the pin wiggling that I'm doing at the moment, the 2 hertz or the 1 hertz, whatever it is, I think it's more like 1 hertz, is too slow, and it's pulling us off. So let us reduce that by 10 times, shall we? I think that's probably even too slow still, but we can give it a go, see what the scope does then. Bring that back. No. Still not behaving. Do even more? No. That's really, really annoying. Give that a hard time. Nah, it's okay. I can see both sides. I mean, I like the open side in that if I'm contributing to an open source project, I'll try my best to use KiCad or whatever. But if I'm working, then typically I'll pick Altium because I kind of fell into it more. KiCad wasn't quite there when I started out. I don't think. That might be me talking from a point of ignorance. I gave it a jolly good go, I think, but yeah. Anyway, no fighting, no need. I don't mind. It's all good. But what we are going to do now is figure out. So if we have a 250 bit, actually 125 bit is a reasonable bit rate, and that is 8 microseconds. So what does 8 microseconds come to? 1/8 minus 6. Sorry, what am I trying to do? 48 megahertz divided by 125 kilohertz is 384. So let's really, really tighten these up. There we go. So this is now kind of in the range of what you might see on a slowish CAN bus in terms of how fast that pin is wiggling. It's wiggling and the scope is showing nothing. Let's just perhaps check that our scope is actually wired up. I mean, it's seeing a midway voltage, and if I put a message on there, does it see it? The other end sees it, but the scope might not be triggering. Let me go and push the button. There we go, so this will now only trigger on a frame. Oops, pushing all the wrong things. There we go, so it does see the frame. Lots of curvy bits going on there. Yes, now, okay, so in terms of the wiggling, what I'm trying to say is that this box here deals with generating the biasing and the assertion on the bus. So when you transmit, when you write or you assert your transmit bit here, the chip will then assert dominance or recessive state on the bus. But if you sit there in a dominant state for too long, then I think this chip will actually remove you from the bus so that you can't lock up halfway through a message and then destroy communication from everyone else. Kind of a safety thing again. So this is part of why CAN is designed the way it is. If we have a look here, I think it'll probably say it up front somewhere. Data rate's down to 10 kbit per second. So drive a dominant timeout, DTO. And that will, yeah, okay, so you get some, less than 1 millisecond would be fast enough to probably avoid that. So we got something else going on. If we take a look at the schematic, we've got pin 1 is the transmit pin, which is just there. So I could try poking it, see what happens. Probably not a bad idea, to be honest. Let's just confirm that we are going to the right place. Oops. Different tools have different mouse controls. Okay, so it's this pin over here. And that via and that LED, of course. So I can poke at that via, I think, or I can poke at this pin here, which is actually the well, calling it the resistor. Let me get another probe. This is going to come up green on the scope, and I'm going to put it right down the bottom. About that big, that's fine. We can trigger on the green wire. Okay. We then poke that. What do we see? To get it in there. We see wiggle, wiggle, wiggle. So that's looking good. Oh, sorry, you can't see that. How's that? There we go. Wiggle, wiggle, wiggle. So that's good. But on the output, we see nothing. Go back to auto trigger. Confirm that's stable. That's stable. Oh, this is annoying. So having a look here again, we've got I could cut that trace potentially. I don't want to. Pin 5 is what? Let me get rid of that one. Pin 5 is genuinely, I think, a not connect. No connect. Oh, it might have been the so it's no connect here, or it's the IO level voltage for the other parts. Now, okay, this is a question then. Is this a part which expects an IO supply? I'm gonna have to get my loop. And it's missing. Where is it? There it is. Okay. If we have a look, this is marked up as a 1051V TI88J 1051V TI88J, I think I said. 1015V. Yeah, P5NV. Oh, I'm wondering. P5NV. Okay, what have we got here then? Markings. That would be really annoying, wouldn't it? Wasn't really planning on doing much soldering in this stream, so I'm not really set up for it, unfortunately. I have to admit, I do hate these data sheets sometimes when the markings are just not listed clearly. TI88J. No. If anyone sees it, shout at me. Sorry, you're not even looking at the screen. How can you shout at me if you're not looking at the screen? I'm just searching through the datasheet to try and find the markings, because they don't put the full part number on top of these devices. Usually they have a list somewhere. Well, sometimes they don't, and it's really annoying when they don't. You have to go searching elsewhere. If you see the right, so on top of the part we've got 1051V. Do you not have the package you got the part in? Oh, I see what you're saying. Yeah, okay, that's a good idea. Have a little rummage in the box. we go. CAN 1051 GV, which is, well, yeah. You'll never be too sure, can you? There we go. No, not that one. Related links, not helpful. Okie dokie, see you, thanks for joining us. There we go. This is a 1051 GV, which is this one. 1051 GV. And that is 5 megabit, 3 volt level shifter integrated. No! Why would you do that? What did I order? I kind of wonder how sensible it might be to just always connect that pin 5 to a known supply. Sad trombone. Let's have a look. Not that one. This one. I ordered this one. I'd ordered the HG, I think. And the HG, 70k volts, 5 megabit. Ah. Well, that's annoying. That might be the end of the stream for today. I didn't want it to end like that. Yeah, that's true. So the package is marked up. You can 1051 GV DRB TQ1, which is just annoying. I could bodgewire it. Not really set up or in the mood or anything for that today, which is a lame excuse, I know. So I think what we basically have now is I was expecting this part on the left, or this pin out on the left, sorry, and we've ended up with this pin out on the right. So pin 5 VIO is not connected on the layout that we've done. So that's this one here, add 5. And I think that should probably be tied to 3.3 or even 5 volts. Probably 5 volts given the interface we're using. I am just going to do one last check. I'm going to do it off screen, I'm afraid, because of personal details and stuff. Have a look at the order I put in, just to get confirmation in terms of what I actually ordered. I need the non-V part, yeah. Yeah. Oh, hang on, what? No, I did. I ordered exactly what they delivered. Oh, that's so annoying. Okay, never mind. I don't think we can even do reception. Even can't do transmit, can't do receive. Can we do anything? I'll tell you what we can do, and this is not what I was planning on doing at all, but I have these neat tools. Oh no, let me extract it from my current work desk. It's not actually in use, it's just the plate that I need to extract. Okay, what do we know about SensePeak, anybody? So these are flexible magnetic doodads. So I could quite probably, with a needle, put 5 volts in that. I'll pod you with this just for tonight. I think so. Gotta find the rest of the pack now. Here it is. Yeah, let's do it. I've not really used the logic elements of these yet. Where are they? I thought they were in here. I've used it for the scope side of things. Ah, here they are. Yeah, so you get these cool little bags. Let me turn the lights on again as well. Okay, so you get these nice needle-tipped things. An excuse to play, isn't it, really, this? So, there we go. Whoops. Needles going flying. Put that back in there. 1, 2, 3, 4, yeah, that's fine. Okay, you get these. And they have a pogo pin needle on the end. And they have just standard sort of 100 thou pins there. And you can whiz them onto the end. And then you just position them really carefully. And they stand up and do what they need to do. And they've actually been brilliant. I've used them quite a bit for scope, oscilloscope use. But I did also get the bits for just multimeter or logic or, slow speed signal stuff as well. So let's do that. Hopefully we can get that on the pad and we can get the 5 volt supply in there as well. Let's check just very quickly before I blow something up that it's okay with 5 volts on there. Yep, up to 7 volts is absolute maximum. Up to 5.5 volts for the I/O, so that's cool. Let's do that. I need to grab myself a wire. I'm going to inject it with this. There we go. Okay. I'm going to put Glasgow to safe state, so just running Glasgow safe will just set everything to sort of a known good all ports safe state. And then if we grab the 5 volt supply from port 2, put that onto our nose here, and then if we just very carefully poke it onto the pad. The pad we need is that one there, which is that one there. That's all right, we can do that. That goes to here-ish. Oh, need some light. That's my torch gun, here it is. Okay. I am hopeful that we now have 5 volts onto the I/O pin. And if we then run, let me put the trigger mode back onto the can. Yeah. Okay, if we run that now, all these. I don't know why this is hanging around. Here we go. Port, so we want port A and B now. And we can run that like this. What do we get? Building, building, building. Wiggles! Yes, look at that! Okay, so that's awesome. And you can even see in here, we got the blue and the green LED going as well, which is cool. Let's just turn those lights off again. There you go. Now, the blue and green LEDs are going, so that's transmit and receive together. Because of what CAN is, as I mentioned earlier, it's this 2-wire bus. When you go dominant on the bus, you see that yourself, so it kind of comes back at you. But that's okay. That's fine. We just need to be aware of it when we're writing the rest of the gateway. If we slow this down, I should be able to demonstrate the the what's it called, the device lockout or timeout or whatever it's called. There we go. That's quite slow, but we can go slower. Let's go really, really slow. What's that? 12, 1, 2, 3. Okay, so that's back to the... Can't do counting. There we go. That's back to the 1 Hertz signal. And I think what we'll find is that we'll get about a millisecond pulse and then it will go recessive again. Hopefully. Let's just tweak the scope quickly. There you go. Ooh, I'll do that for you. So what we see here is then, if I just do cursors, every approximately 500 milliseconds, so that's our 1 Hertz pulse. We then zoom in, we get a 1.74-ish millisecond high period. And that then covers the timeout that I was talking about earlier. So the transceiver will actually remove you from the bus if you're not actually sending any data, if you just get stuck. So that's cool. Brilliant. I'm happy. And you can see that, again, in terms of here, I'm not sure if you can actually quite see that the transmit LED is a 50% duty cycle, but the RX LED is a very brief blink. I don't think you can quite see that, unfortunately. But yeah, there you go. Next, what are we doing next? We want to confirm that we can see the receive pin now. So I'm just going to take some notes, I think. The termination pin, this pin has a shorted indication LED. More generically, we've ordered and fitted the -V variant. Oops. Okay. Transmit works. Now we want to do the receive. So for this one, what we can do, I think, is should we wiggle the termination LED but put that on the second channel? You can. That's cool. Okay. So I'll bring you back to here. I'm just going to put some comments in there. And I think what I'm going to do now is on the receive, when the bus gets asserted, I'm going to latch that onto the termination thing, and we can then see that on the LED, but we're going to assign that to channel 2 instead of channel 1, just so that we can see something happening. So we're going to take self CAN bus term O equals term O, and how do we do an OR? We do a logic OR like that, bitwise OR. Self CAN bus dot RXI, and what that's going to do is it will just latch it on. So if we put pin term onto pin 6, so that will then use the orange LED on the other side. Okay. Oh, it's come on straight away. That's annoying. Okay, let's bring our counter back. While we're counting, do that. Turn it off. Okay, so it will latch it on for the duration of the count, and then I'll turn it off again. So turn it off once a second, and hopefully that will cover our startups date. Nope. I know what the problem is. we actually want that to be the inverse of, because it's a logic 1 while the bus is recessive. And that should then just be off. And hopefully we can send a message and turn it on. Okay. So hopefully you can see that. This LED down here, the orange one, is off. And if I now send a message, I'm going to queue it up. So it's just can send, can 0, 1, 2, 3, 1, 1. Queue it up, and then I'll send it while you're watching there. Oh no, it didn't turn on. Oh, it did turn on. Yep. I just caught it wrong. Cool. So we've confirmed now that the transmit and the receive work when we inject power, which is cool. I'm just going to resync this again. Wait for it to freeze. Get it going again. Oop. Yeah, that's better. Okay. Goodness me. Not a particularly smooth startup, was it? Or bring up, or whatever you want to call it. Now, if we are going to send a message from somewhere else and then receive it here, we need to understand how bit timings work. And with the UARTs, it's generally best to sample the line at about 50% of the bit time. But with CAN, there is a whole bunch of other stuff involved as well that they like you to do. I don't think it's talked about at all on this. Oh, here we go. So, yeah, okay, you get the sync period, and then you get the propagation period, and then you get phase 1, phase 2. So the state of the signal changes at t equals 0. The sync period then covers, I think it's just allowing the bit to actually happen. So you might have seen earlier on the scope that there are quite sort of slopey looking lines, and that's because of the capacitance and or resistance termination, etc. on the bus. So this just lets the bit take effect, and then the propagation, so the prop is allowing the bit to go all the way down the bus and reflect back, and then you get the phase 1, phase 2, and this then is the 50% sample point of that. And that can be tweaked up and down depending on your bus or your driver or whatever it is you need or want. This is talked about in the CAN spec. So if I just grab that up quickly. And I think it's probably worth referring to this a bit now. Probably going to be going for another hour or so, I think, and just see where we get to in that time. Right, so part A is the, what is it? I thought it was the low level side of things. I think it is, yeah, here we go. Start frame. Ding, ding, ding. Okay, and then part B was what? Oh yeah, part B is the application there, so that's like what you actually do with the contents, I think, as well. I thought there was talk about these. It's in the end. Okay, interesting. I thought this was much earlier in the spec. So synchronization segment, propagation, and then phase 1 and 2. Okay. So if we are going for, let's go for 250 kbit initially. 250 kbits per second. That means that we have what per bit? We've got 1 over 250 kbit is 4 microseconds. 4 microseconds per bit. And we want to then split that up into these periods. I thought there was some words about how long. So sync segment is 1 time quantum long. Propagation segment is programmable between 1 and 8. Phase 1 is, again, 1 and 8. And phase 2 is the maximum of phase 1 and the information processing time. Oh, I think it's just the rest then, isn't it? The time quantum is a fixed unit. There are... Okay, I don't think in that case it's between 1 and 32 quanta per bit, I think in that case. And if we come back here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's just follow that, I think, for now. Which means that we want 400 nanoseconds per quanta. And 400 nanoseconds is what, given that we've got 48 megahertz clock. That's 20 nanoseconds per tick. 400 nanoseconds, milli-micro nano, divided by that is 19.2. So if we go for, just hard coding this now, about 19 ticks per quanta. Is that going to do us okay, I think? Let's just check that out. So 400 nanoseconds times 19 times 10, I think we were after, is 76 microseconds. What have I done wrong? Oh, sorry, okay, so let's start that again. 48 megahertz. 1 over 48 megahertz is 20.8 nanoseconds. We've got 19 of them per quanta, gives us about 400, so that's 395 nanoseconds. And we've got 10 of those per bit is, 3.9 microseconds. That's fine, cool. So bit psych is going to be, 19. That then means that we get 1 for the sync. We get 3 for the propagation. Phase 1 is 3, phase 2 is 3. What are they actually called? Seg 1, 3, seg 2 is 3. Oops. So what we want to do, is make a state machine now, which takes care of counting through. The sample point is between these two. Sample point is here, and the bits change, or whatever you want to call it, the signal change is here. Okay, so we start at the idle state, which is a logic 1, which is the recessive state for the bus. So I'm just going to call that idle. And then if we see a bit or a transition to the asserted dominant state, that's a logic 0 on the bus, then we need to advance into the beginning of the bit time here. So that would be self can bus dot rxi equals 0. So if it goes low, n dot next equals bit a, let's call it, I think. Now we need to wait, so we need to put the counter, got a 32-bit counter already, so md sync counter equals 0. And we now need to wait until that counter gets to sync plus prop plus tseg. And we're not being too cautious about how we're handling that yet. If the counter is greater than equal to sync plus prop plus seg 1. When we start transmitting on the bus, we're going to have to care much more about how we do this, but for just sniffing, I think this is fine. Bit B. Okay. And this is then going to wait for the rest of the time period to expire. I think let's just keep counting up. Plus seg2. And that then goes back to bit A. So that then wiggles backwards and forwards. And that will then sample each bit. Now in here, aside from advancing onto the next state, we also want to sample the bit. Part of the problem with CAN is that it is not actually very friendly when it comes to storing this in bytes. You've got an 11-bit arbitration field. You've got a 1-bit remote, 1-bit extended ID, 1-bit reserved, 4-bit, I can't remember what they are, control field, and then 8 to 32, is it? 64? Yeah, 64 bits of data, so they are octets, that's nice. And then you've got a 15-bit CRC, you've got a CRC delimiter followed by acknowledge, etc. And then you've got interframe spacing there. So the arbitration field is the ID that I've been referring to earlier, and that's 11 bits. And I think the best thing to do then is store that into a 16-bit field. The DL0 through 3, I can't remember what those are. Let me just look them up in here, see if they're listed. I'm pretty sure they will be. In the control field, data length, of course. Yeah, okay, so that tells you how many bytes you've got. A DL, so this is 0001 is a decimal value of 1, and that says you've got 1 byte of data. And that can go up to 8. So we need to store the arbitration field, we need to store the length of the data, capture all the data, and then grab the CRC, and then kind of expect it to finish, and we need to sort of handle the end of the frame as well. So how are we going to do this? I kind of want to have a state machine in this state machine. I'm not quite sure how's best to do that just yet. Any ideas welcome, of course. So what I'm going to do, I think, is just suck all of this into 8-bit chunks and pass it up to the computer. Start frame counts as the first bit, I think, doesn't it? So, oopsie. What we're going to do now is shift the data in. So cat, I hate this, I always get confused. Can we check on the UARTs to figure out which way this needs to go? It's either least significant bit first or most significant bit first. So that's a good start. We've only got 2. I think it's most significant first here. That'll be data 1 to 0. Oh, sorry, 1 and onwards. Yeah. With the self.can bus RXI on the end of it. Okay. So we're going to count each bit in, and then it with if data I is greater than or equal to 8. We need to put it on the FIFO and run away. I think that works, doesn't it? just refer to this for putting it on the FIFO. Yeah. And then let's clear the data again. So we're going to sample it, shift it in, and send it to the PC. We're going to need to have something to pull it out the FIFO at the other end in a minute. And that's just going to keep running as soon as it's triggered, which is not ideal. If we have a look at, not that one, this one, and have a look at the scope, I'll zoom in a bit for you. So this is what we are sending at the moment. Oh, that's annoying. There you go. You can see the decoder at the bottom there. So I don't think we have any full 8-bit segments of this, which are all 0. So I'm going to just say all 1, sorry. So what I'm going to say is if that byte is all 1s, then we're going to stop and we're going to go back to idle. Oops. I don't want m.data. I'm getting tired. If it's all 1s, m.next equals idle. So that should allow it to stop once it gets to the end of the packet. Just really hacky, nasty yuck at the moment, but that's kind of all right. Make it do something first. I'd like to break out the bit time and sampling from the rest of the logic, in terms of packet handling and stuff. But yeah, let's maybe get onto that in a sec. In terms of grabbing data out of the UART on the PC side, we need to do interact TGY gets the UART. UART's then going to give us some. Oh, it's forward, okay, yep. That's why I couldn't see it. That's then going to give us the FIFO handles. That seems to be just read and write, which was not what I expected. Okay. Well, let's give that a go then. So in the bottom here, we need to interact and we need to do while true UART.read. So that's our data. I'm just going to print it. I'm going to print it with a O2X on the end, I think. Oops. Get rid of this. And I think that'll block as well, so that's nice. It's probably going to blow up. Yep, it did blow up. Unexpected keyword max. Okay. Oh, of course, we need to give it a range. That's old syntax from ye olde mygen. Grab some water. Oh, never awaited. Okay, oops. So we need to, I think, await that. Oops. Right. Yep, it's good. So that's now running. What do you reckon will happen if we put a frame on the bus? Do you reckon it's going to come through? Excuse me. So, this is nerve-wracking, isn't it? Put that over there. Oh, no! Unsupported format, of course, because that's giving us a lump of data, not a single byte. So let's call that buff. Oops. And then 4b in buff, I think will do what we're after. Oop. Oh, look at that. We got a whole bunch of data with some stuff in it. I don't think we're counting the bit time properly, are we? No, we're really not. We are counting individual clocks rather than multiples of 19 clocks. So that needs to be times bit psych. Let's try that again. Still not great. Lots of FFs and 00s, which was not the plan. Do we take some inspiration from the UART, possibly? How does it handle the separation for the UART? Let's split these. Split off the UART bus is the individual signals, but I thought there was also another module which took care of like the state. Oh, it is this one here. Okay. In that case, what we need to do is, I think I've got it in my brain now. Let's just get rid of everything else. I'm going to make another one. I'm going to call it CAN, I don't know, low level elaboratable. We want to have the bus. I think nothing else right now. In here, we're going to set up some signals. So we're going to have the sample point, sample ready maybe. And that will tell the outer system when it should be sampling the bus. We want something pretty similar to that. And we're going to count individual bit times. Now, if we refer back to the wiki page, someone's got to trigger us, and then someone's got to tell us to keep going, I think. Probably the best way to do this. So the trigger is going to be the bus going dominant. And the keep going is going to be possibly a timeout paired with we're expecting more data. It's probably not ideal, but I think it'll go. Trigger. Trigger actually wants to not be that. It wants to be the bus.rx, isn't it? RXI. Continued signal. It doesn't want to be called continue, it wants to be called run. Why not? Okay. that actually wants to be equals 0, and therefore it's just the inverse of that. If self.trigger, the counter is reset to 0, we advance onto the bit phase 1, let's call it. Counter then gets incremented every time, and if we cross the sample point, or we run up to the sample point, we're going to want to set self.sampleReady equals 1. So that tells someone else to go and have a look at the bus. I think that's okay. We can change this for bit phase 2 and get rid of all of this, I think. And then in bit phase 2, we want to keep counting. And then here, if we don't want to keep going, then we return to idle. Otherwise, we continue back to bit phase 1. So if not self.run idle. And that will go to bit phase 1. I think that works. Need to add that as a submodule. I'm going to call it LL. And we can then hook into that from here. We also need to move that counter across. I'm going to put these notes in there as well. There we go. Okay. That sound reasonable? Okay, where you at? Go look at this again. On the RX side, you've got the data. Oh, this actually handles all of the data framing, but we're not quite able to do that, I don't think. The RX ready. RX ACK is what? Okay, because we're taking data out of its latches. Yeah. This just takes care of the sample point in the bit. I'm going to rename sample ready to RX ready, I think. And I'm also going to call that RX run. RX trigger. No. Okay. Now then, we want to hook these two together. Not quite sure how to do that yet. But instead of the idle bit A, bit B that we had previously, we're going to want to do the more sort of structured approach, which is outlined here. So we've got the arbitration, the control, the data, count them down, and then the CRC. So with M state is idle. I'm going to pass on that for now. And we're going to do the arbitration. Control. Data. CRC. should be able to calculate that in the FPGA as well, which would be quite cool. I'm going to call that the ACK. And then the end of frame. So now we should have a good sort of flow through here. We're going to have a counter. I'm going to make these massive just because I'm lazy for now. And if the low level tells us to go, RX trigger, then we move. There we go. I think what we're also going to do is connect the low-level RX run to fsm.ongoing, is it? Idle. Apart from we want to invert that. So while it's not idle, we get the other side, the low-level module, to just keep running. And when we come back to the idle state, we let it peter out and stop. I think that's good. Okay, in the arbitration field, we need to count 1 bit for the start frame. Let's put that in as well, because start frame. Otherwise, we'll get sort of lost. Start frame. Okay, that's 1 bit. So as soon as we see low level dot RX ready, we can just advance. We don't care. Okay, so for the arbitration, we need to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've got the 11 bits for the ID and the 12th bit for the remote flag. And I'm actually going to split this into 2, so ID and remote, like that. Hopefully this doesn't feel silly to anyone that's watching. Hope it's kind of making sense and stuff. Not had anyone talking for a while, I feel a bit lonely. Give me a wave. Okay, so reset the counter and count down from 11. I'm actually going to set the counter to 11 and count down to 0. Hey everybody! Thanks for waving back. I never quite know if people have dozed off or something. Oh, thanks everybody. Okay, we're going to have a signal here, which is going to be the ID. No, I can't call it that. So let's call it arb_ID, signal 11 bits. And we're going to shuffle it along every time the RX ready state happens. And that is going to be, what's it going to be? It's a cat again, but as you might be able to tell, arb_ID. Let's also just clear that quickly as well. Set it to, oops. Sorry, I keep fumbling my keyboard. It's annoying. arb_ID equals 0, so let's just wipe that out. Yeah, honestly, R&D, I think I put myself under. I don't work directly with cars and stuff, but I do have customers and people that do that. I've done industrial stuff and I've done automotive stuff with CAN, but I don't have a particular area as such. call this bus, I think. Am I allowed to use bus? That is not a reserved word, is it? Bus equals that. Bus.rxi. Okay. Oh no, we need to put that in here. And therefore we can join these two together, make it look a bit cleaner. We also then at this point can say if the counter is equal to 0, then move on. And to replace the expensive canoe hardware. Oh, I don't know. I think, to be honest, my expectations of CAN with Glasgow are that we could do some pretty interesting things. Because of what Glasgow is and what it can do, we could potentially very easily sort of force someone else off the bus. So as soon as we see their ID coming on, we can then stomp on it and sort of get privilege over them, kind of thing. Or we could stomp on their data and corrupt checksums, or this kind of thing. And you can kind of test the bus and the systems on the bus from a much more analytical and sort of careful environment than you might otherwise be able to. So I don't think I would use Glasgow to work with CAN, but I would most likely use it to debug and to test and to do all the other things as well. Or instead, sorry. Make sure that the other stuff is behaving properly. There are certain rules with CAN, like if you, I think it's if you receive a certain number of messages with an invalid checksum, you're no longer allowed to transmit on the bus. And again, this rolls into the whole sort of automotive safety, resilient, robust, whatever you want to call it, side of things, where if you're seeing that many messages with an invalid checksum, there's got to be a reason, and the reason could well be that you're not very well connected. Vault injection, exactly, yeah. Not sure about compliance, but I suppose from a CAN compliance point of view, it could well work, yeah. Anyway, so first up, we need to, on here is grab the remote flag. So this just says remote. Oops. This just says if it's can't actually remember. The remote flag says if it's destined for me or destined for you. So if I am requesting data from you, I can set this bit, and I will then sort of hope for you to put your data on the bus at some point later. Okay, so that's cool. I think now we've got the control. This is, again, going to split probably into a number of phases. So you've got the extended ID, you've got the reserved, and then you've got the data length, 4 bits. So let's do next ID. This is who is supposed to be filling the message, or just a general request for later. Is that at me, Omni? Or is that not at me? Now that's why it's all gone wonky. In terms of pulling data in, I guess I could do this in a much cleaner way, really. This whole section here is always the same. I'm not sure if they've got a... Yeah, they have. Here we go. Ooh, nice. Okay, if you have an extended ID... Oh no, that's not what I wanted, sorry. That's bit stuffing. Oh, they don't have a nice picture of an extended ID. I'm not going to deal with extended IDs right now, but if you have an extended ID, basically you add a further 18 bits onto your ID, and that comes where? That's the 11 bits of ID, 1 bit of remote request. Oh, it's a substitute remote request, and then it's 1 bit of ID extension, and then 18 bits of extended ID, and then the real remote transmit, and then a reserved, and then the DLC. So yeah, sort of in here, you get a whole bunch more ID bits. So this first chunk here could be dealt with really cleanly, and then the rest of it could be based on that value, I guess. I'm going to ignore it and keep it all separate for now, though, I think. For the reserved bit, we just move straight on. Don't keep it, we don't do anything with it, we just move over it. Then we got the DLC. And this wants to be 4 bits worth, so a 4 in there. Start using this. No problem. Thanks for coming along. Sorry it might be a bit late with you, but I hope it has been enjoyable, interesting, whatever. Right, so we want DLC in here as well. And that's a 4-bit field. Oops. What have we done with the ARB ID? Yeah, we have cleared that out, so let's do that here as well. So that's control DLC equals 0. I don't think we need to clear them out because we are shifting the full amount through, but never mind, let's just do it. Oh, I haven't done this properly, have I? ARB ID equals that. And let's do then control DLC equals that. Okay. Once we got to the end of the DLC, we are into the data. It's not arbitration anymore, it's just data. We need to now count for 8 times the value of the DLC. And every 8 bits we should transmit it up. So then, that's 11 bits, let's call it 16. Or 11, 12, 13, 14, 15, 16. Oh, it doesn't quite fit. 11, 12, 13, 14, 15, 16. Yeah, we could fit the ID, the remote request, ignore the extended ID, and the 4 bits of control into 2 bytes. Is that worth doing? I think it might be. We can transmit the first bit at the end of the arbitration field. Oh, sorry, at the end, yeah, at the end of the arbitration, or at the end of the ID even. Again, this is kind of hacky. I'd like it to be somewhere else, I think. Oops. UART. See what they do in there. There it is. memory jog for the FIFOs. So we are going to cat, actually no, we're not going to cat anything, we're just going to do the arb ID, okay, because this is being shifted through, that means we can just take the bottom 8 bits, I think. All right. Hey, welcome back. I'm confusing myself again with the bit ordering in MyGen. So that is actually backwards, I think, to how bits are ordered. But what I'm trying to do now is just test. Yeah, so that will go up to, but not including the 4, and that will go up to, not including the 8. Okay, in FIFO, write, ready, enable. This one, I think that's all we need to do. So that's going to ship off the first 8 bits of the ID, and then once we get to the end of the DLC, we can do the next chunk, and that's going to be concatenation of the arb ID. We're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2. So 0 to 2. We're going to have the remote request. And we're going to have the DLC, all 4 bits. I think that will come out to an 8-bit word. Write that off to the host. Now for the data, we want to set the counter. How's that going to handle that? I think it will deal with it, won't it? In terms of, I'm trying to set the counter here, and I'm also trying to set the counter here. I think MyGen will deal with that nicely, which is good. I just realised that that's probably possibly causing us an issue in a couple of places. Oh, maybe not. It's because of how things are laid out. It's an issue now. Let's put an 8-bit counter on that. We want to then count down 8 times, and each time we want to decrement the value of the DLC. So with the RX ready, so the data is going to be the same as before, so from data 1 to the end, followed by plus RXI. And if the counter is 0, then we're going to ship the data off, and we're going to decrement the DLC. Or is it control DLC, or? Yeah, it is control DLC, whoops. Control DLC, like that. So that's going to be equal to -1. We're going to ship the data off. And what else are we going to do? Yes, if the DLC equals 0, then we are going to hop over to the CRC. Now, this doesn't handle the situation where the DLC is 0 at the beginning and there's no data. So I think that's going to have to come in here. That's okay. Yeah, okay. Let's grab the data field as well. So that's going to be an 8-bit data field. Data signal 8. Now the CRC is 15 bits. That's a bit icky, but whatever. So what we want to do in here is have the counter set up ready to go. 15. And then there's a CRC delimiter followed by an acknowledge. Yeah. I don't know, I feel like this should work. Low confidence, unfortunately. Oh, I probably want to clear the CRC as well, don't I? CRC. Yeah, CRC equals cat CRC 1:0 and bus RXI. How big is it? 15-bit, I think it was. Yep. CTR counter. After this CRC, okay, we're going to want to transmit twice, I think. First time we're going to want to transmit after the first 8 bits, and the second time after the next 7. So I'm going to do this 2 times. If the counter is 7, then we've got 7 bits remaining, I think. We're going to transmit self in FIFO. And we're going to need to truncate that to the first 8 bits. And then if it's 0, so that's the end of it, we're going to do cat a const. I'm about to do these. The compact guide, isn't it? That's what I'm after. Compact summary. That's the wrong repository. Ah. Where's the margin gone? Never mind. Const. Oh no, it's not compact summary I'm after. Tell you what, let's have a rummage in. Oops. Where are we going? Can't remember. Where is Enmagen. Oh, it's an egg. Oh. Okay. That's not what I wanted. There we go. Let's grab that. Oh, whoops. Didn't want to do that. Hit uninstall. Yes. There we go. Now, in here somewhere we should find const, and I could have sworn there was a way to give it a width. Reset signal and signal.width. I think I can do C tags in here. There we go. Init. Value shape. Okay. Oh, and then shape can be unsigned and the width that I want. I think, is that right? Const value 0, unsigned 1, I think. Unsigned width, yeah, that will do. Right, okay, apologies for the diversion there. So that'd be that, followed by the CRC 7 bits. And then we move on to CRC, what was it called? Delimiter. I'm just going to ignore the ACK, I think. And there's an ACK delim. I'm not going to store it and share it or anything, I'm just going to ignore it, pretend it's good. And then we go to the end of frame, and that's got 7 bits, and then we got inter frame separator, which is 3 bits. Yep. End of frame. I also want to do m.d.sync counter equals, was it 7? 7 bits. So the end of frame counts for 7. And then we got the interframe separator, IFS. I'm not sure if that's always 3, but I'm going to pretend it is just for now. And then we return to idle. Okay. I think we're there, maybe? Is it going to work? Unlikely. Unlikely, I feel. That's not what I want to do. I want to make that a value of 3. Okay. We've caught everything. We're trying to give it to the host. I'm just going to say go and see where it blows up, I think. How does everyone else feel about that? There's quite a lot there, isn't there? Come on then. Gonna explode. Ah, 104. That was unexpected. Do I have to say plus equals and LL equals rather than plus equals? Because then it gets all unhappy and confused about who's who. Okay, invalid syntax 135. 135. M.say, right, okay. Need to get rid of that, that's simple. 168. Probably the same again, yep. I'm a bit of a muppet. 187. Ah, I'm ashamed I didn't spot that. Right, driver conflict. This is what I was concerned about. Already driven from, oh, MD comb, okay. Where are we? We're on line 191. So who, okay. Trying to drive signal W data from desync, but it's already driven from combinational. Ah, yes, okay. Split that there. Do that. Same again. On line 211. There we go. This needs to be combinational. Same again here. No way. Oh, look at that. Okay. And we send a message. Oh, we got lots of garbage this time, which is nice. I'm still not convinced that we're doing the bit times correctly. Kind of tempted to try and do something about that. This is where it would be very nice to do a trace. So let's do a trace. If I can remember how. It is just trace. Can sniff BCD. Running, running, running. Try and get in there quickly, otherwise we're going to massive trace. It's quite a long time to load as well, which is a bit frustrating. There you go. Okay. Pictures. There we go. Oops. Oops. Wasn't me. Please go away. Open a new one, and we're looking in Glasgow CAN, and we're looking in Glasgow software. Glasgow. No, where are we? Glasgow software. Oh, Sigrock. Oh, hang on. Yep, sorry, forgot about that. I need to choose the other type. Can sniff, okay. Sure. That's not what I'd hoped to see. better. No, it's still short. We have a little bit of a wiggle on the RXIO there. But we also don't have all the other signals which I was hoping to find. I think I might need to go away and have a play with this some other time. Okay. What I'm going to do is I'm going to wiggle the what's it called? The term pin here. So we can see where we are sampling. I think I've shared pads. Oh, bus. Term out equals 1. Yeah, so that should turn that on. It has no bus? Oh, no, okay. I didn't catch it. If we look carefully while I run this, okay, we saw it blink very briefly. If I then send a message, oh, we're not. Why have I overrun shutting down? Oh, what have I done? Did I just wiggle that pin off? No, that looks okay. Oh, it's the analyzer is shutting down. Oh, let's turn off the tracing. There's too much going on. Now when I send this message, I'm kind of hoping to see that orange term LED blink, and I don't. Have I not put it on the right pin? And I have, pin 6. That's okay. Could just be very brief. No worries, Omni. It's good to see you. Thanks for coming along. See you again next time, hopefully. Right. Let's get the scope back, I think. In fact, I'll put you on the scope. Turn that channel back on. And I think every time I run this, we should get a new capture. If I poke the term signal, or sorry, the term LED, will we see it blink faster than you can? We do, look at that, okay. Oh. Got it one time. It's stuck now. Let's stop it and start it again. Oop. No. Have I fallen off? But fundamentally, from what we saw just now, there we go, we can be confident that we are going way too fast. So I need to have a think about that. I'm just going to take a quick pause if that's all right with everybody. I shall be back very soon. Okay, bye. I have returned. Okay, so where were we? We have the clock, or the sample points are just way too fast. I'm going to go and play with the scope for a sec. See if we can determine what's going on there. Let's grab the cursors and have a look, see if we can determine what this is here. Actually, we're particularly interested in the green, but it's coming through into all the other signals as well. So that is 25 megahertz. That's way too fast. "25 megahertz. Where's that coming from then? Okay, if we come into the sources again, here, let's write these calculations out in full. We have 250 kbit per second, which brings us to 250 kbit per second is 4 microseconds, agreed? That's 4 microseconds per bit. What we actually want is 10 quanta per bit, 10 time quantas. So that brings us down to, divide by 10, 400 millimicro nanoseconds. 400 millimicro nanoseconds, yeah. Okay, I'm just writing the same thing as what's below, unfortunately. Now, we have a 48 megahertz clock in Glasgow at the moment, and if we turn that into time, that is 20.8 nanoseconds. We've got 400 nanoseconds as the target. Divide by 20.8. Oops, 400 nanoseconds. Millimicro nanoseconds divided by that is 19.2 periods per quanta. So that all hangs together. The bit cycle is 19. In terms of the actual framing, here we go. We're recreating this from the wiki page. So that's a sync period, 1 time quanta, propagation is 3, phase 1 is 3, phase 2 is 3, and you sample between phase 1 and phase 2. So if we have a look here, we got sync is 1, propagation is 3, phase or segment 1 is 3, sample, and segment 2 is 3. Okay. Oh, I know exactly what the problem is. We've never reset the counter. Oh, dear me. So, what we're doing here is we are being triggered by the bus being asserted or going to what's it called, dominant state, and that resets the counter to 0 and brings us into phase 1. Phase 1 then sits there counting diligently up to the 32-bit up to 1 plus 3 plus 3, which is 7 times 19, which is, anybody? 7 times 19 is 133. So that will count there to 133. Let's put extra brackets in just to be sure. 133. At which point it pulses the RX ready signal, which is fine, and it pulses the termination. That's what we were watching with the scope. And then we move on to bit phase 2. So this ready flag is when the other part of the code will then take a sample of that of the line. Then we do more counting up until we get to seg1 plus seg2 times bit cycles. So that's going to be, let's just put bracket there, just for clarity or whatever you want to call it. Now we've got 10 times 19 is 190 ticks. Times that by 20.8 nanoseconds is 3.952 microseconds, which is exactly what we're after. Well, it's not exactly, but it's near enough what we're after. At which point, if we are not being asked to run anymore, we return to idle, so we stop looking for bits and start triggering again. If we are being asked to run, then we go back to phase 1. And actually, we could merge these phases into one because, yeah, the same thing really, isn't it? Maybe. How does that work? That's all good, I think. So that, I think, hopefully will resolve the issue. Oh no. Oh, phase 1 is referenced but not used. Or not thinged. So don't change that, and we need to change this. There we go. Okay. No, thank you. Oh, what does it look like? Oh no, nothing. Okay. Put my probe on the scope. Oh, sorry, put my probe on the termination LED again. What do we see? Oh. Here goes logic high and stays there. That was unexpected. I wonder if I've just dislodged the power. We were injecting it with the sensor peak tool. Okay, start Glasgow again. Seems to think it's receiving at the moment, which is not right. Oh. Okay, we got a bunch of data. What's going on now? Let's rework this just to be a little bit more clear. No, I don't want to do that. I did want it. Oh, I see. Okay. The issue is exactly that. Let's put equals in there instead. I'm never very comfortable with equals. I always think, what happens if you go past? But I think the issue there was we're just falling into the first one over and over again. Maybe. Maybe not. We're getting nothing again. Okay. Let's break them up into 2 states again. I'm just going to put this here. So when the termination LED goes on, that's when we sample it. When it goes off again, that's the bit change, or the expected point of the bit change, or going back to idle. That's debug stuff. Let's just put that down here. Why is this not working? Okay. Nope. Unhappy. Not open file. No such file directory. What? think I've seen this before, where the tools fail and their error doesn't come out. I don't remember what it was, although it doesn't look like undoing it has fixed it. Just do this quickly, see if that, if that helps. Yes, it did. Okay. So I think there's something broken about what I've just written here. But I don't know what. That's annoying. Could I just delete all of those? Yeah. Is there a log output or anything? I don't know enough about this, unfortunately. Nope. Okay. Oops, bisect it instead, see what happens. Yeah, that works. So it's probably in here. Get rid of this, do you reckon that'll work? Yes. How about get rid of that? What? That looks fine. What's the problem? Okay, so the problem is mdsync counter equals 0. I mean, that's not special, is it? Counter equals 0. I mean, that looks identical. Let's put it into bit done state. Phase. State, yeah. Like that. Are you going to be happy with that? Yes, seemingly. What? Never mind. Okay. Send a message, you get nothing out. You get nothing out at all. RX run, I think, was set to, yeah, the ongoing there. So while we're not in idle, then you ask it to keep going, which is fine. I don't want to use RX trigger there, I want to use RX ready. don't think that's the problem. I've removed now the debug thingy that I had in here. And I was using the self bus.term O equals 1. Work. Come on. Okay, so that works. If I then run it, or send it a message, nothing. And if I probe that line, we see nothing either. I think the power supply for this might be a little bit unhappy, to be honest. Is that what it is? Oh, that looks very promising. Okay. Yes, it does indeed. Right. What do we see? What do we see? Oh gosh, I think the issue just now was mainly to do with the probe I'm using to power the transceiver, because that's now seemingly working quite nicely. I'm getting the same data each time. Okay, let's grab that and let's try and decode it and check that it works or it looks sensible. The frame we're sending is this, which is address 123. DLC is going to be 1, and data 0 is going to be hex 11. These are all hex. And then CRC and stuff. Okay. So let us work out what that actually is. So the address 123, if you look on the scope, we can see that we've got 123 coming through as, I think it's most significant bit first. So 123 in binary. Oh, we've got bit stuffing going on, I think, potentially, which is going to be causing us some pain now. Joy, okay. Let's just and send. Let's just interrogate this quickly, just check that it's doing what I think it is. CAN ID is 3 SFF. Oh, standard frame versus extended frame. Okay, so they are hex characters. Okay, so 123 is hex. It is indeed hex. And that comes out to be in binary 3, 2, 1. Like that. This is 8, 9, 10, 11, 12 bits. I'm going to knock off 1 bit there. And that means that we should see 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. And if we look at the scope, we see, let me zoom in on that for you. We see a 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. So that looks good. If we then consult the code we've written and try and figure out what it's actually sending to us, we get the arbitration ID, and that is being shifted in left first, or leftwards. So the bits are being shifted in least significant bit, 1 by 1. Where have I gone with everything? I've got too many things open now. Get rid of some calculators. Get rid of some schematics. Probably done with most of these. For today at least. And with these probably too. Okay. Now I had to. And with that. There we go, much better. So the 1, 2, I think maps directly onto the 1, 2, 3. Which is good. The 2, 9 then is going to be, I think, because what did I do? Oh, okay, I remember now. I merged some bits together, didn't I? That's probably not the most sensible thing to have done in hindsight when we're trying to read it. There we go. So we got the 3 bits of the 3 bits of arbitration ID, the remote flag, and the DLC in here. So that is OB 10 9, like that. That's going to be, I think this is most significant bit first, so 3 bits of that. That looks wrong immediately. Remote is 0, and the DLC is 4 bits. Oh dear. Off again. Let me rework this, I think. I want to send the arbitration ID in parts. And I'm going to put const on the front of this. 0 unsigned some number of bits. It'll probably pad it out for me, but I don't want to be unknown. So that's 4, 5, 6, 7, 8, 3 bits of 0 on the front of that. Okay, here, counter starts at 11. So if we go 11 minus 8 is going to be 3. All right. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Yeah. So when this is 3, we want to omit the first 8 bits, correct? Oh, well, actually, I think we've lost some bits there. And when it's then down to 0, we want to omit the first 3 bits. That's going to be 5 bits wide. So the DLC and the remote flag are going to come together. Let's give that a go. No, can't do 158. Extra bracket. There we go. Okay. Send a message. We get this in. I wonder if we're 1 bit out. I think it might be time to stop this stream and come back to it another day. Hopefully next Wednesday. Just trying to understand exactly where the bits are and whether bit stuffing is important for us right now to consider. I think it probably isn't. I think we've got enough transitions in there. Yeah. Oh, hey, Alan. Just waking up, are you? I was probably just about to stop, unfortunately. We've got, I think, most of a frame very hackily, nastily decoded and being transmitted back to the host PC in octets, in bytes. I still need to fully understand what we're actually getting out. I think that it's possible the bits are I think these bytes here might be 1 bit out of phase and possibly also shifted in the wrong way, perhaps. I need to have a think about it. This is something that always trips me up when I'm dealing with NMyGen. I will, just before I go though, I'm going to send a few messages and see if we can see it change. So there's, let's do ID 1 with a payload of 00. Didn't like that at all, did it? What? Wrong CAN frame format. Do I need to give it 3 bits? Or three, there we go, 3 characters. You woke up early and I'm just going away, I'm sorry. Yeah, so loads of Fs there, unfortunately. But if I change that 1 for 2, do we see a... Yeah, see, that's not right. It's changing 2 bytes instead of just the 1. And it's changing them quite significantly, actually. It's going from AO to 20. Oh! 233 people from Strange Parts. Thank you very much. Welcome, welcome. I'm very, very sorry, but I was actually just about to head off. We've been playing with Glasgow this evening, and we have got so I've got the CAN add-on module or add-on board, whatever you want to call it here, which we found one bug in that I didn't wire one of the chips up properly. But aside from that, we've got it working to some degree. Oh, brilliant! You've been playing with Glasgow as well. What have you been playing with? So yeah, we've got the CAN is receiving data and it's transmitting it to us in this horrible format, and it doesn't look good. It's in a pretty unhappy state. So we will have to figure that out, I think, next time probably. So what I'm expecting here is address 1, and then 1, 2, 3, 4, 5 bytes of payload. And then if we do 6 bytes of payload, what do we get? We get this. So yeah, that's just not very happy, because this one on the right hand side is supposed to be longer than the one on the left. Oh, sorry. There you go. Yeah, so yeah, we've been playing with the Glasgow, playing with CAN, trying to get it working. Very relevant. That's very good to hear. I'd love to hear more about what you're planning to do with CAN. I'm gonna have to read back through the chat. There's loads of people here. Welcome, everybody. I try to keep on top of it, but yeah, sometimes I forget to bring the camera to the right focus. Oh, that's triggering too many times now. Let's just go and tweak that quickly. Yeah, there you go. Not ready to talk about your plans for CAN, that's fair enough. Yeah. Anyway, I think that's me for today, and very sorry to be running away just as everybody joins. Thank you for raiding Strange Parts. That's very kind of you. An I2C driver from scratch. Are you thinking of a micro or Linux or quite what? Yeah, Glasgow is actually fantastic, and I was going to mention this before I left. So this is what we've been working with today. This is the on the left is the Glasgow CAN add-on that I've been working on. Designed it on stream, built it a couple of weeks ago, and this is the first time we've actually powered it up and started to get it working. This is a Glasgow Rev C1, which I built a small batch of a little while ago, and a whole bunch of people have hopefully had their hands on and are enjoying it now. I am going to be giving a talk at FOSDEM next weekend on the 7th of February, I think it is. So if you feel like you might like to join FOSDEM and talk about Glasgow, ask some questions, you'd be more than welcome to join. Peter or Esden will be joining me in the talk as well, and we'll just be just talking about Glasgow. And Esden will be covering the DFM work he's been doing to get the campaign up and running. See if I can just grab the schedule really quickly. There we go. So here we are, Glasgow Digital Interface Explorer. We are at 5:15, and I believe this is where are they this year? Belgium, something like that. I can't remember now. I think it's +1. I'll be tweeting about it. So if you feel like following me, you'll be able to have a sort of a notification via Twitter. I'm sure Peter will be mentioning it as well as potentially a lot of other people. So yeah. Oh, thank you very much, Peter. By Strange Parts. I've forgotten your name. Is it Scotty? I think it's Scotty. It's probably not Scotty. Anyway. Oh, Omni, you're not all the way upside down, are you? It's it is. It's +1. There you go. Tooltip tells all. Anyway, that's it for today, I'm afraid. Thank you, everybody, and do please join us for FOSDEM. It'll be a great talk, and there'll be, the way I understand it is there's going to be the talk, then some Q&A, and then there'll be sort of a hallway chat, which might be a little bit more relaxed. I'm not quite sure how it's going to work online, but please feel free to come and have a look. Thank you all, and see you soon. Bye-bye.